Now let's apply this formula of integration by substitution on this expression of probability. So we can find, based on that and based on what I've just explained, we can find a variable y such that this expression is equal to y of a to the integral from y of a to y of b f of x of y multiplied by d of x of y divided by d of y multiplied by d of y. Now, what we should note here is that this term right here is a function of y. This thing is a function of y. Just remember how we have transformed this integral to this integral. So this term that we got at the end was a function of y. Therefore, I can say that this is equal to g of y. So let me write this whole term again. So this will be equal to the integral from y of a to y of b. Let me write it, actually, I think it's going to be more convenient if I write it in the next page. So this would be equal to y of a to y of b, from y of a to y of b, the integral of the function g of y, d of y. And this, based on that definition of probability of the random variable x, we can say that this is equal to the probability of the random variable y such that y is included between y of b and y of a. So why I'm doing this now? Why I'm writing this in terms why I proved that this is equal to this? Because I want to consider this function as, I want to have the right to consider this function g of y as a probability density function. So this is just the probability density function of the variable y. So g of y, based on this equality, g of y is equal. So now I'm not interested anymore in writing x with respect to y. So I'm going to just express g of y with respect to, in terms of f of x, d of x, and d of y. So g of y is equal to f of x multiplied by d of x divided by d of y. So this is what I was looking for from the beginning. This is the relation between the probability density function of x, which is the pixel value in the original image, and this is the probability density function of the new image or the enhanced image. And here the terms, or the two variables x and y, have appeared in this formula. So my goal is to get y in terms of x, because this is the mapping function I'm looking for. So y is going to be equal, so this is d of y is going to be equal to f of x divided by g of y multiplied by d of x. Remember, g of y is a constant. Here, I said that in order to get an image with a good histogram, or an image with a good contrast, its probability density function should be as uniform as possible, which is in this case continuous. So the amplitude of this function is 1 divided by 255, which is a constant value. So here d of y, or y, is going to be equal to 255 integral of the function f of x d of x from 0 to x. And for the consistency, just not to get confused of the variables, we replace x with another variable, for example w or z. So this would be f of z d of z. Now, this is the mapping function I've been looking for, y of x. And this is its expression. Now this expression, let's make this expression a little bit more general. So I can write y of x is equal to L minus 1 sorry, L minus 1, the integral from 0 to x of f of z d of z. And L in this case represent the possible gray levels of an image. So for an 8-bit image, L is equal to 2 to the power 8, which is 256. That's it. So that's the proof of this formula, the proof of the formula of the global histogram equalization that we use to enhance the contrast of images.